Good morning, everyone. Welcome to this video lecture on Module 3 Time Response Analysis and Steady State Error. So, in my previous video lecture, we have gone through the time response analysis. We have defined what is transient time, okay, what is a steady state response. So, based on this time response and steady state response, today we will go for what is steady state error. Basically, what we have discussed in the previous class regarding the steady state is it is the signal or it is the state which lies after the transient response and dies off after some time interval t, and both the time response, transient response and the steady state response are with respect to time t. Okay, so today here we'll go to steady state analysis and we'll try to analyze the signal, which are basically the five different signals which we have seen yesterday, that is step signal, ramp signal, parabolic and sinusoidal signals and impulse signals. So here today we'll go with the another type of analysis, it is steady state analysis. So in the yesterday's class, we have seen some time intervals. One was the rise time, the other was the overshoot, maximum overshoot, then the settling time. So here, before going for the study of this steady state analysis, here we have the following two specifications. The specifications are nothing but how much time the system takes to reach its steady state is nothing but settling times. Once you apply the input to some control system, that system will function with respect to time t, and after some time interval t, the system will reach to its steady state, and that state is called as settling time. Okay, and we have one more here is the steady state error. It is represented by ess. Okay, and we define the steady state error by how far the actual output is reached from its desired value. I've given a few examples on the actual output and the desired output. So therefore, we basically define the steady state error as it is the difference between the actual output and the desired output. Now today we'll go for the derivation, how the steady state analysis can be carried out using some mathematical equations. So before defining the mathematical equations here, we need to know the Laplace. So as we are familiar with the Laplace domain, okay, and how to convert those Laplace domain. We have defined this error signal or the difference signal is by E of S in Laplace domain, which is equal to R of S minus C of S into H of S. Okay, so now let us see the derivation for steady state error and how we can minimize the error. So if I consider this figure, that is 7.6, which is a closed loop system with a negative feedback. If I consider this block diagram or a system which has an input R of S, output C of S, an error signal represented by E of S, and a feedback represented by B of S. We can see here how we are trying to find the equations. To find the equation B of S, we multiply the output of the system to the feedback. So B of S is equal to C of S multiplied by H of S. Similarly, we have an equation for E of S represented by R of S minus B of S. So now if I substitute the value of B of S in E of S, I get E of S is equal to R of S minus C of S into H of S. And the output signal is represented by the multiplication of these two, that is C of S is equal to E of S multiplied by G of S. So therefore, signal E of S and C of S are defined. Now substitute the value of C of S in the above equation. So we get E of S, that is the error signal, is equal to R of S minus C of S is E of S multiplied by G of S. into h of s. So in this way, we find the error signal. Now, it is also possible to find the input signal, that is R of S. So R of S is equal to E of S plus E of S, G of S and H of S. So I got the other side of the equation. So the reason here is we are just separating the input signal to the error signals. So if I want to find only the error signal, then let us take a common here. So E of S, if I take common, it becomes E of S multiplied by 1 plus is equal to E of S multiplied by, or it's E of S multiplied by 1 plus G of S multiplied by H of S. This is my E. If I take E of S as a common, okay, then R of S will be as it is. So therefore E of S, if I keep it on the left side itself, then the whole block of 1 plus G of S into H of S will move into the denominator of the R of S. So the error signal is given by E of S is equal to R of S divided by 1 plus G of S multiplied by H of S for a non-unity feedback. It is called non-unity because in this particular diagram we have a feedback represented by H of S block. So if I want to make my system a unity feedback, then I will just remove this H of S and simply connect one normal line. So during that condition, your system function error signal is represented by R of S divided by 1 plus G of S, and H of S is equal to 1. So therefore, we have obtained the equation for E of S. Now, this E of S is in the Laplace domain. That is the reason it is expressed in terms of S. Now, if I want to calculate the error value, this particular error value, then in time domain, now it is in the S domain or the Laplace domain. Now, if I want to make it into the time domain, then this E of L will become E of t. Now, if you want to find the steady state error for this particular E of t, then it is given by the formula, the steady state error ESS. ESS here represents steady state. So the steady state error is equal to limit t tends to infinity of E of t. So here E of t is my error signal, and we need to find the steady state for this particular E of t. Now, using the final value theorem, which states that if my limit is tends to infinity for f of t, then in S domain it becomes limit s tends to 0 s multiplied by f of s, s multiplied by f of s. So therefore, using the concept of final value theorem and applying the final value theorem for this steady state error, we get, that is ESS is equal to limit t tends to infinity of E of t becomes limit s tends to 0 E multiplied by E of s, where E of s is the Laplace transform of E of t. Now if I substitute the E of s value here in the derivation, so I get the E of s is equal to, this will remain as it is, that is limit s tends to 0 will be as it is, your s will be as it is, but instead of E of s, you substitute this value, that is R of s divided by 1 plus G of s multiplied by H of s. We can see here, after substituting the value of E of s, we get the equation for error, that is steady state error. Now it is limit s tends to 0, s multiplied by R of s into 1 plus G of s into H of s. This is for non-unity feedback. If it becomes for a unity feedback, then it becomes s multiplied by R of s divided by 1 plus G of s, because H of s is equal to 1. Now, for this particular the steady state error, this equation can be concluded that the steady state error depends on, or on what values of the r and g and h. The value depends on steady state here is, it depends on r of s. We can see because in the numerator we have a value of r of s. R of s is equal to, it is the reference input, okay, and it has g of s into h of s. It is nothing but your open loop transfer function and the dominant non-linearity present if any. So in this way, your steady state error can be obtained. So you may get an question with respect to steady state error. Define the steady state response and derive the equation for steady state error. So you just draw that figure and try to derive this equation and apply the Laplace transform. Now, once we study the concept of steady state error, now let us apply the steady state error to find the the various uh, other values or the other signals what we have seen in the yesterday's class. So what can be the effect of input on the steady state errors? For example, if I consider the figure 7.7 here, in this 7.707 I have applied an input signal like this, and it is just getting settled down. This is my actual input here, but this is my the desired output. So I need to find the steady state error for this particular signal. Now you can see here there is one line drawn here representing it by a letter A. So that letter A represents my unit step signal. As we have seen in the previous class, the unit step signal is being represented by A divided by S. A represents the magnitude. So therefore, my input R of S becomes A divided by S. So if I apply my R of S as a reference input to a control system, then to find the steady state error for this particular input signal, we get limit s tends to 0, s multiplied by r of s 1 plus g of s into h of s. Substitute the value of r of s in this equation. So if I substitute, it becomes limit s tends to 0, a multiplied by, so s multiplied by a divided by s divided by 1 plus g of s into s. This s and the denominator s get cancels. The equation we obtained here is limit s tends to 0, a divided by 1 plus g of s into h of s. As the a is the magnitude of the input signal, which is a constant, so therefore the steady state error or a unit step signal is given by ESS is equal to A divided by 1, because again it's a constant, plus limit s tends to 0, g of s into h of s. So you need to only apply the limit to this g of s and h of s. Similarly, for a system, if you have a constant here like g of s into h of s, then it will be called as positional error coefficient. I repeat, for a system, if you have a limit which tends to 0, if you apply it to g of s into h of s, which is a constant number, then it is called positional error coefficient, and it is represented by Kp. So therefore, what is the value of Kp now? So Kp is equal to this particular value, that is limit s tends to 0, g of s into h of s, which is equal to my positional error coefficient. So this particular equation of E of s, now it can be replaced by this equation. You can see the equation, that is E of s is equal to A divided by 1 plus Kp, where Kp is equal to limit s tends to 0 divided by g of s into h of s. Okay, so this is one example. We have applied the steady state for a unit step signal. Similarly, you can do it for the other signals. So for the other signals, if I take as a ramp signal, the another test input signal which I can apply it is for a ramp signal. We know the input to the ramp is given by A divided by S square. So how to find the steady state error for this particular ramp signal is take the standard formula for the steady state error represented by E of SS. ESS is equal to limit S tends to 0, S into R of S divided by 1 plus G of S into H of S. Fine. Now substitute the value of R of S in this equation. So we get limit S tends to 0, S multiplied by A by S square divided by 1 plus G of S into H of S. One S in the numerator and in the denominator get cancels. So it becomes A divided by, okay, the value in the denominator is in the numerator is goes to the denominator. So therefore, limit S tends to 0, A divided by S multiplied by 1 plus G of S into H of S. Okay. Now, we can open the bracket here. We get A divided by, this is S multiplied by 1 is S, right? So S plus S into G of S into H of S. Now after opening the brackets, now apply the limits to the above equation. So if I applied the limits as A is constant, so it becomes E of SS is equal to A divided by, if I apply the limit for S, so this becomes S tends to 0. So therefore, A divided by limit S tends to 0, S multiplied by G of S into H of S. Now, we have this particular value for a selected system. If it is a ramp signal, then the limit can be written as limit S tends to 0, S multiplied by G of S into H of S is a constant. And this constant is called as velocity error coefficient. So in the, if it is a step signal, it becomes a positional error coefficient. If it is a ramp signal, it becomes velocity error coefficient. Now, to represent the velocity coefficient, we take it as kV. So kV is equal to limit S tends to 0, S multiplied by G of S into H of S. So the modified equation for E of SS, this becomes A divided by kV. You can see here the corresponding error is represented by ESS is equal to A divided by kV. So this is the another derivation if the input to the control system is your ramp signal. Similarly, we do have one more type of test input signal, which is your parabolic signal or a parabolic input, whose magnitude is represented by A divided by 2 into t square. Now, if I take my R of t is equal to A by 2 into R of t, and if I convert this into the Laplace domain, it becomes A divided by S cube. Now, substitute the value of R of S in this equation. So we get limit S tends to 0, that is A multiplied by A by S cube divided by 1 plus G of S into H of S. So one S in the numerator and the denominator get cancels. So it becomes A divided by S square, and this S square goes to the denominator. So now it becomes limit S tends to 0, A divided by S square multiplied by 1 plus G of S into H of S. Now open the bracket, it becomes S square plus S square into G of S into H of S. Now apply the limits. So if I apply the limits, it becomes A divided by S square plus G of S into H of S. Now this value of the limit now can be rewritten as E of SS, or simply the limit which is tends to 0, S square into G of S into H of S is again is a constant, and we call it as an acceleration constant represented by K A, K suffix A. Now Ka is equal to this particular value. Now if I substitute the value of Ka in this E of Ss signal, so it becomes E of Ss is equal to A divided by Ka. So we have applied the three inputs to the control system. One is your positional error constant coefficient, the second is the velocity, and the third is acceleration. So if you look at this particular table, if you want to calculate the static error coefficient, if it is a Kp, which is for position, Kv is for the velocity, and Ka is for acceleration. And for that particular, we have a formula. If it is a position, it is limit s tends to 0, g of s into s of s. If it is velocity, s of s multiplied by g of s into s of s. If it is acceleration, it becomes s square into g of s into h of s. And the corresponding steady state error is represented by ESS. For Kp, we have 1 A divided by 1 plus Kp. For Kv, we have A by Kv, and for Ka, we have A divided by Ka, where A denotes the magnitude of the applied input. So in this way, we try to go for finding the error for the different values of different signal. Similarly, based on these values, we can have what should be the effect of change in G of S and H of S. If I change the value of G of S and H of S in all these coefficients, then do it have any kind of impact, or do it have any kind of effect on the open loop system? So let us check with how the steady state error can be applied to various type of systems. So before going for the type of system, let us take the elements, that is G of S and H of S, from the error point of view. For example, if you have a constant represented by K, and you have a poles, that is G of S into S of H of S at origin, and because if you take any transfer function, the numerator represents my zeros and the denominator represents my poles. So if you take a standard formula for this particular steady state error, this is my numerator and the denominator. So the denominator represents my poles. So if these poles, that is G of S and H of S, if they are taken at the origin point, then that particular can be formed as a time constant. So it is expressed as, now G of S is equal G of S into H of S. We get the new formula for G of S and H of S is equal to K, okay, which is a constant multiplied by 1 plus T1S, 1 plus T2S, and so on. Similarly, in the denominator, we have S suffix I, or can be J, that is 1 plus Ta into S, then 1 plus Tb into S, it goes on, like 1 plus Tc into S goes on. And this Sj, S raised to the power of J, is nothing but it's the type of system. Basically, we do have the various type of system here. They are, if the value of J is equal to 1, or if the value of J is equal to 0, or if the value of J is equal to 2. So if J is equal to 0, it becomes type 0 system, type 1 system. If J is 2, type 2 system. If J is n, we represent it by type n system. So therefore, by the definition of the transfer function, that is, it is the Laplace transform of G of S divided by 1 plus or minus G of S into H of S. So in this way, we find the order of the transfer function, or the highest power of S represents the which is represented in the denominator polynomial of a closed loop system. That is why it is more required to define the type of system. So basically, in the control system, we will come across type 0, type 1, and type 2 system. So in the next class, we will see how this type 0, 1 and 2 system can be analyzed for the various values of K and the various values of Ka, Kp and Kv respectively. Thank you.